Alright, so in this video, I'm going to solve the equation 1 to the power of x is equal to 2. So, before we even start solving this, if, let's say x is equal to 1, then I have 1 to the power of 1, which is equal to 1. And if x is equal to 2, then I have 1 to the power of 2, which is also equal to 1. And you can go even 1 to the power of 10 is still equal to 1. So you may be thinking, what possible value of x can make 1 to the power of x equal to 2? So let's try solving this. What I'm first going to do is start by taking ln of both sides. So I get ln of 1 to the power of x is equal to ln of 2. And ln is the same thing as the natural log. And the reason I took the ln on both sides is because it comes with a property that states that if I have something in the form ln a to the power of b, I can move this exponent b to the front, so this turns into b times ln a. So in this case, I have ln 1 to the power of x, and I can move x to the front. So I get x times ln 1 is equal to ln 2. And you may be thinking, we could just divide both sides by ln 1 and x would equal ln 2 over ln 1. However, the only problem with this is that ln 1 is equal to 0. And remember, anything divided by 0 is undefined, so this would be undefined. So we know that this equation has no real solution, but it could still have imaginary solutions. So to actually solve this, I'm going to use something known as Euler's formula. And basically what this formula is if I have something in the form e to the power of I times theta, this is equal to cosine of theta plus I times sine of theta. And I know to many of you watching this video, this may just sound like a bunch of gibberish, but just hang on. So let's say that theta is equal to 0, right? Say that theta equals 0. So now I get e to the power of I times 0 is equal to cosine of 0 plus I times sine of 0. Cosine of 0 is 1 and sine of 0 is 0. So I get this all is equal to 1. Now, what if we say theta is equal to 2k pi? And k is just a substitution for all real numbers. So now I get e to the power of I times 2k pi is equal to 1. Because all we did was we just substituted theta in for 2k pi into this same thing. So now, because this is equal to 1, we can remember our first equation, which we started with 1 to the power of x equals 2, we can substitute in this for 1, meaning I get e to the power of I times 2k pi to the power of x is equal to 2. So just think of this as 1. So I have basically 1 to the power of x equals 2. And now, with this, I'm going to take the ln, or natural log, on both sides. So I have ln e to the power of I times 2k pi to the power of x is equal to 2. So I'm going to now bring this x down using the property of natural logarithms. So I get x times ln e to the power of I times 2k pi is equal to 2. is equal to ln of 2, because if you take ln on one side, you have to do the other side. And now I can also move I times 2k pi to the front. So I have I times 2k pi times x times ln e is equal to ln 2. ln e is simply equal to 1. So I get x is equal to ln 2 over I times 2k pi. And now I'm going to multiply this by I over I. So I get x is equal to negative I times ln 2 over 2k pi, because I squared is negative 1. So this is my solution. Alright, so in this video, I'm going to be solving the equation 5 to the power of x is equal to 50. So to first start with this problem, let's test different values of x. So if x is 1, then I get 5 to the power of 1, which is equal to 5. And this is too low. Now if x equals 2, I get 5 to the power of 2, which is 25. And this again is too low. Now if x equals 3, then I have 5 to the power of 3, which is 125. And this is way too high. So we know that the value of x is going to be somewhere in between 2 and 3, meaning it's going to be a decimal. So how are we going to find the exact value of x? Well, to start, we're going to be using logarithms. So I'm going to take the log on both sides, so I get log 5 to the power of x is equal to log 50. And the reason I'm doing this is because logarithms come with a special property that state that if I have something in the form log a to the power of b, I can actually move the exponent b to the front, so this turns into b times log a. So in this case, I have log 5 to the power of x, and we can think of x as b, and I can move this x to the front, so now I get x times log 5 is equal to log 50. And now remember, we want to find the value of x, so all we have to do that is to get rid of this log 5 by dividing both sides by log 5. So now these two cancel out, and I get x is equal to log 50 over log 5. And now, let's simplify this a little to get the exact decimal value. So log 50 is the same thing as log of 10 times 5. And another property of logarithms is that if I have something in the form log of a times b, this is equal to log a plus log b. So now this turns into log 10 plus log 5 over log 5, which is the same thing as log 10 over log 5 plus log 5 over log 5, which is just 1. And log 10 is also equal to 1. So I get x equals 1 over log 5 plus 1. So now, all that's left to do is do 1 divided by log 5 in my calculator. So I get x is equal to 1.431 plus 1, which is equal to 2.431. So this is my answer.